Okay, everybody. Today we're going to look at how to do a hypothesis test to compare two different population proportions. So I've got this example here about drug testing of high school athletes. So an interesting fact is that in 2002, the Supreme Court ruled that schools could do random drug testing of students who were participating in after-school activities like athletics. You can't just randomly drug test all the students, but if they want to do something extra like be on the football team, then I guess it's okay for schools to do random drug testing. And so the question that comes up is, does that work? Does that help reduce the percent of students who are using drugs? And so here's data that was collected from two similar high schools in Oregon, one of which had random drug testing of athletes, and the other one did not. And so we're going to look at the results of a confidential survey here, where at the school with drug testing, only 7 out of 135 of the randomly selected athletes admitted that they were using drugs, illegal drugs that is. And at the other high school where they did not do random drug testing, it was 27 out of 141. And so we have two variables here. One is explanatory and one is the response variable. So if you pause the video, you can think about which one is which. Okay, so now my answer to which one is which is that we want to know if students are using drugs, and we think that something might affect that decision, right? And that's the drug testing. So the drug testing would be explanatory, so I would just enter that in as explanatory is drug testing, whether the schools did random drug testing or not, and then the response variable is drug use, were people using illegal drugs. And now we haven't done two-way tables in a while, but now that we're comparing two different population proportions, this is a natural situation to put your data into a two-way table. So let me go ahead and set this up. So in my two-way table, I usually like to put the explanatory variable on the top. So either the school was doing drug testing or it was not. So let me make two columns here. And not testing. And then if they were doing drug testing, some students used drugs, and so maybe make a little more space for that. Used drugs, and some students didn't. And so here are the numbers. So at the school with drug testing, that was Watonka High School, it was 7 students admitted to using drugs. So we put the number 7 there. And that means that of the 135 total athletes, I guess if you take away 7 from that, it's 128 that did not. And then at the other school, 27 students admitted to using drugs. And then if you take that away from 41, let's see, what is that? That's 114 left that were not using drugs. And then it's a good idea to add in the totals here for this two-way table. So the totals would be down here, total, and that's 135, and the other one is 141. Assuming I subtracted right, that should be the right numbers. Okay, great. So here's a two-way table. I've got the explanatory variable, whether they were using drug testing at the high school at the top, and then I've got the response variable over here on the side about whether the students were using drugs or not using drugs. Okay. So now we've got the perfect situation for a two-sample hypothesis test for proportions, because we want to know, does the drug testing make a significant difference, right? It looks like it's making a difference. It's only 7 out of 135 versus 27 out of 141. But is that difference significant? And that's where the hypothesis test will come in. By the way, before I do the hypothesis test, I should probably pull up a calculator and actually calculate what the two percentages actually are. So let's see, what is 7 out of 135? No, that's wrong. Clear that. 7 divided by, where's the division symbol? There it is. No, that's a plus. Undo that. Divided by 135 is 5%. Okay, so That's about 5.1%. And then the other percentage, actually if I round it, it's 5.18, which is closer to 5.2%. And then this other one, 27 divided by its total is 27 divided by 141. So again, these are column percentages. 141 works out to about 19.1%. So yeah, it's a way higher percentage. 19.1% is way more students using drugs, student athletes admitting to using drugs than the school with random drug testing. So it looks like it's making a difference. But then, is it really, or could this have just been a fluke, right? That's where a hypothesis test will come in. That's what a hypothesis test is designed to do, to tell us if sample data like this is real evidence of a difference or if it's just something that could have been a random fluke. Okay, so the null hypothesis. It suggests in the problem that you should use a null hypothesis H0 that uses these two symbols. PT for the school's percentage of students at schools with testing who do drugs, and PN for the percentage of students at schools that don't test that do drugs. And so one hypothesis would be that there's no difference, right? And that's your null hypothesis right there. So P subscript T is no different, so it's equal to P subscript N. Perfect, that's the null. And then the alternative is that, yeah, actually maybe there is a difference. And if you just think about it for a second, you can probably guess which way the direction goes, right? If you do testing, why are you doing testing? It's, well, you're hoping to convince students not to do drugs because there will be consequences if they get caught. And so the proportion who do drugs, the P, should be lower if you do testing, so it should be less than if you don't do testing. Sort of, if it's going to go one way at all, that's the direction it should go, right? Okay, common sense. So if you can use common sense, then you can do a one-sided alternative instead of a two-sided not equal to alternative. Okay, perfect. So there's our hypotheses. We're done with number 2. So we move on to number 3. It says use the two-sample hypothesis test formula. And before you can do that, you're going to need to find the pooled proportion p hat, right? So p hat, this is new. This is something we haven't seen before. This is when you have two different samples, like this one. You have all the students in the first school, it was 7 who used drugs out of 135, and then you had all the students in the other school, and 27 of those out of 141. And neither one of these is the right proportion if the null hypothesis is true. If the null hypothesis is true, we should have the same percentage in both schools, and our samples weren't the same. This was 5.2%, this was 19.1%, so neither one of these is the right percentage. But the null hypothesis is just saying that the population proportion should be the same, not these two sample proportions. So these could just be randomly off target a little bit. So we need a good guess about what the population proportion should be if these two populations are really the same. And so the best guess we could come up with is if we could combine all of our data together into one big data set. And so I should probably add one more column to my table, a totals column, and let's see what the totals are here. So the total for the first row is 7 plus 27 adds up to 34. Okay, so that's the total number of successes. In this case, a quote-unquote success is whether a student is using drugs, right? So what we call a success in statistics isn't necessarily a subjective judgment of what's a good outcome. Okay, and then I could add these two numbers together to get the total number of failures. That looks like 200, and what is this? 14 plus 28 is, what is that? 42, I think. And then the last one, adding these two numbers together, is 276. So there we go. So the combined proportion of all the students who admitted to using drugs is 34 out of 276. And so that's our p hat. So p hat, and when since we're doing this all online, when you type your answers, it's okay with me if you just type p hat. That's a nice way to write that. P hat is the percentage 34 divided by 276. So 34 divided by 276. And if you want to use a calculator to calculate that, you can, but you don't have to. It's okay to leave it as a fraction. So 34 divided by 276 is 12.3%. So that's our pooled proportion. If you're going to enter this into the hypothesis test formula, you do have to enter it as a decimal. You can't enter 12.3 because that's not the right answer. That'll give you an incorrect answer. And my interactive formula sheet can't handle percentage symbols, so don't try that. Either put it in as a fraction or put it in as a decimal. But you can write your answer at the end as a percentage. But that's just a shorthand notation to make it easier to read. Okay, so now number 4, use the two-sample hypothesis test formula. So use this thing. And again, you are always allowed to use that interactive formula sheet, or you can just use a calculator. The calculator, you do have to be a little bit careful. This is a complicated formula. I recommend splitting it into parts. I'm going to be lazy and just use the interactive formula sheet. So the interactive formula sheet, we're on the last 2 formulas this week. So we're talking about two-sample z-value formula for proportions. So here it is. And I've got all my numbers. I've got proportion 1. I just have to find it. So I go back to the workshop. Where's proportion 1 here? Well, that's this one. It's the proportion in the testing school who admitted to using drugs. It's this 5.2%, or probably better to just enter it as the fraction 7 over 135. So there we go. That's what goes there. 7 over 135 is proportion 1. Proportion 2 is the other school, 27 out of 141. And then the p hat without a subscript, you just have to know, this is new knowledge, that's the pooled proportion. So that's everybody all together who said that they used drugs out of everybody all together combined. So the combined sample size was the 276 students total. Then the 2 individual sample sizes were 135 and 141, and we're done. We've got all our numbers, so we hit enter, and there we go. There's our z-value. It's negative 3.53 if you round it. So I come over here, go ahead. It wants the z-value, the test statistics we sometimes call this. So our test statistic is negative 3.53, and of course this is a bell curve. We're talking about something that's 3.5 standard deviations below average. If you remember anything about bell curves, you know that that's going to be off the charts. But let's just go ahead and check it anyway. So here's our standard bell curve with a middle at 0 and a standard deviation 1. That's what we use whenever we work with z-values. And so my z-value is the location, negative 3.53. And I want the tail, which is the stuff that's even below that. So the probability of getting a result that's even lower than that is this, and there it is. It's a p-value of 0.0002. So I can even copy that. So the p-value equals 0.00021. And is that below 5%? Yeah, that's way below 5%. It's way below 1%. So this is very, very significant. So it's very, very significant evidence. But what is it evidence for? So we're talking about drug testing. We want to know if drug testing works. We had a null hypothesis that said, no, it wouldn't make any difference. The proportion of students using drugs would be the same at schools with testing and at schools without testing. And now we have evidence that suggests that if that were true, then the probability of seeing a result as extreme or more than one we saw, right? That's what a p-value is, would be astronomically tiny. So this result we're seeing, where 19% of the students at the school without drug testing admitted to using drugs and only 5% of the students with drug testing did, that's not a fluke. That p-value is so low, I just can't believe that this is a fluke. So this is real evidence that we should do what? Well, it's evidence that we should reject the null hypothesis. Low p-values are strong evidence that the null hypothesis is probably wrong. So we reject it, we go with the alternative, and that means that drug testing works. So we come over here to our conclusion. So that's it. Very significant evidence that drug testing reduces the percent of students using drugs, or some similar conclusion. All right, now there's one more worry here. We do have to double check that all of the assumptions check out. So first of all, we do have to worry about whether the normal distribution was an appropriate thing to use in the first place. As long as our sample sizes were decent, and in this case our sample sizes were actually pretty big. It was 128 students here and 135 students here and 141 there. Those are pretty decent sample sizes, but when it comes to proportion techniques, what really matters is the number of successes and failures. And we do only have 7 successes in this group, but actually, according to our book, that's actually okay. As long as all the successes and failure numbers were at least 5, then it's probably safe to do this hypothesis test formula, so we're good to go. So the first assumption that this was normal distributed data is probably actually safe. The other assumption, of course, is that there's no bias in our sample. That could potentially be a problem. These 2 high schools were not randomly selected, although it does say that they, the survey didn't say how they selected the students, but it probably was randomly selected from within the high schools. So as long as the high schools are representative of schools with drug testing and schools without drug testing, then we're probably in good shape. But I'm not sure that that's true, right? It could be that there are other differences between these 2 high schools. All the text here said was that they were similar high schools. I'm not sure that that's good enough to convince me that there weren't other differences, like maybe one school is in a more high crime area, or maybe there's some other demographic differences. I don't know. And because I don't know, I should be worried that that could be a potential confounding variable here. That said, this was, was this a randomized controlled experiment? Did they randomly select students and then decide to do drug testing, or did they just take data that was already available and just observe what happened? In this case, yeah, it's an observational study. They're just taking 2 high schools that are already doing drug testing. They didn't control for all those lurking variables. We haven't really controlled for the location of the high schools, whether there's demographic differences between the student bodies. If you were going to do a randomized experiment, you'd randomly select high schools and then you would assign them to different groups. One high school would be told you have to do drug testing, and one high school would be told you can't do drug testing. And that's not what happened. Okay, so this was just an observational study. That means we can't necessarily prove that the explanatory variable really is the cause. Why? Because there might be lurking variables like we've already discussed. Let's just write that down. You can't prove cause and effect with an observational study. And the reason is because there might be lurking variables that aren't controlled, right? That's the big idea from before the break, right? That explanatory variables might be the cause, but they might not. There might be a lurking variable that's an alternative cause, and unless you can rule out all the lurking variables, which you can do with a randomized experiment, but you can't do in just an observational study like this one. Okay, that's it. That's how you do a hypothesis test. And these hypothesis tests for 2 sample proportions, oftentimes they go with a 2-way table. So we're going to pull out some of our old tricks from the chapter on 2-way tables and the chapter on explanatory and response variables. All of that stuff is relevant again. So we're going to be looking at this stuff. Okay, as always, if you have any questions, let me know.